Let's continue with our bearing capacity lectures. In the first lecture, we talked about some of the basic theory behind the concept behind bearing capacity, the upper and lower bound thing, and plasticity, and the basic formulation of the bearing capacity equations, and some of the workarounds that we do to make them useful with real foundations and real soil profiles. We're going to continue that today, and we're going to talk about some of the other aspects of bearing capacity that we kind of started but didn't really get very deep into. I gave kind of a list of the workarounds I was going to do, and we're going to get them done. So continuing on, we're going to talk about groundwater table and layered soils. You will hopefully recall from soil mechanics that the groundwater, that it is the rare soil stratigraphy that is not layered. You'll also recall that the rare soil capacity has not had enough groundwater in it. And you'll probably also recall the fact that this groundwater table interacts with the layering, and in fact we traditionally split layers based if the groundwater table is present between the boundaries. And because the groundwater table, by changing the effective stress profile and the buoyancy of the water, changes the geotechnical properties and the way the possibilities of any soil layer. So the two kind of go together. The way that this implementation that I'm discussing of the bearing capacity equations goes, however, you would never know that bearing capacity that even looks at layered soils. But that's not the case. We have to consider layered soils. There are three approaches that we've seen over the years in dealing with layered soils. Approach number one is to use the lowest values of shear strength, friction angle, and unit weight below the foundation. It is the simplest, but it is the most conservative. And use groundwater factors in conjunction with that. In other words, you use the groundwater factors I've taught you. You pick the lowest values for the layering below, and you go with it. That's the simplest way. That's the way we're going to start with. The other two ways are a little more complicated. In the past, I've taught the second one. You use a weighted average. Take a weighted average between the base of the foundation and a distance B below it, and you take a weighted average. Well, the only problem with that is that if you have a very soft layer somewhere in there, the soft layer is going to drive the failure of the whole thing. And as a result, it's going to kind of mess up the whole the weighted average won't be low enough, in other words. And in terms of the soil properties you use. So that's the disadvantage of that. If you use, obviously, with engineering judgment and a little experience, a lot of experience maybe, you can overcome that. But for the moment, we're going to stick with this, with the first one. The last one is use a trial surface approach, or what we call it trial wedge and retaining walls, but trial surfaces to see which one is what. Kind of like you do in slope stability, where you examine hundreds and sometimes thousands of different surfaces. That's kind of some of those things that has to be done with the computer, and by the time you do that, you're probably better off doing the fine element analysis if it's that tricky. Most shallow foundations are not that tricky because the whole point of a shallow foundation is just something simple. So you can get that occasionally, though. If you use any actual layering of the soils, whether it's weighted average or you include the effects of the groundwater table, as always. Let's consider an example. And it's really the same examples we had before the last time, except that now the groundwater table is 3 foot below the base of the foundation. Find the bearing capacity. The groundwater factor is based upon the depths, DW, the depth of the water, and the water table is 5 feet below the ground surface. It's 3 feet below the base, and the base is 2 feet below the surface, therefore the water table is 5 feet below the surface. That's an easy thing to overlook, but in the haste of solving problems, but don't. After that, the solution from Table 8-5 in your Soils and Foundations Reference Manual, you have the DW, the CWQ and CW gamma values. At 2 feet, the base of the foundation, the CWQ is 1 and the CW gamma is 1/2. At the point 1.5 plus the base times the base plus the depth of the depth of the foundation, at 9.5 feet, the bottom of the influence zone, it's 1. It's 1 for both of them. So therefore, therefore CWQ is pretty simple. It's 1 at both ends, so it's 1 in the middle. Gamma, you have to interpolate. You get interpolation of 0.7. Once you do that, you plug and chug, as I show you here, and you get an ultimate bearing pressure of 11,280 psf, which represents an 11% decrease over what you had before. Everything else is the same except for the inclusion of the groundwater factors. Let's talk about some of the other workarounds. We've already talked about some workarounds. In fact, we've talked about most of them. The strip footing, the shape factors, the level base, the base inclination factors, the vertical load things, which the load inclination are not really the best way to do that. The homogeneous soil, the groundwater factors, and the related theory we just discussed. And last but not least, the general shear versus local and punching shear, modified C and phi values. The other workarounds we will discuss are as follows: the load eccentricity and the footings on top of slopes. Load eccentricity is unavoidable with foundations. We're going to talk about that first. Loadings are frequently ideal in the ideal world, and a spread footing would never be eccentrically loaded. However, in the real world, they are, and they are for good reasons. If you've got limited real estate and you need additional bearing capacity area under it, you can't always get that concentrically from, say, the columns if the columns are close to something else. So you can sometimes extend them backwards. And sometimes moments get added because of different types of loading and whatnot. You'll get moments. Let's make some definitions. This is one place where I usually lament the fact that vector statics, as is normally taught in engineering schools, doesn't do a lot of justice. These are very simple statics. And so therefore, a lot of the vector statics you learn, we don't apply them that way. It's more simplistic than that. So don't overcomplicate it. Eccentricity, let's start with the definition, is the distance between the effective point of loading to the centroid of the foundation. In other words, the effective point at which we're assuming at this point that all the loads can be resolved to one point load somewhere on the foundation. You can, and there's a number of ways that can happen. For one-way footings, it is from side to side. Obviously, or it can be two-way for square or rectangular frames. In other words, it can be eccentric. You got two different, you've got a B-axis and a L-axis, and it can be eccentric from one or both of those. And we're going to talk about both of those. You can also, if it's just axial loads, down loads like that, and they're not in the center, that's eccentric. But even if a load is concentric and there's a moment, the moment can actually shift the resultant of that load off center. In other words, what we say, instead of trying to, include moments, we just say that, well, the moment moves, take the moment arm and divide, take the moment, divide it by the load, the axial load. You get a moment, because basically that the eccentricity becomes the moment arm. And that's how you get moments out of the system. And that's very helpful. The tricky part is that there are two ways of accounting for eccentricity in structures, for shallow foundations. And we use both of them. Unfortunately, we do. Your book talks about we use the ramp system for structural analysis. That's not entirely true. It's partially true. It's not entirely true. But the other thing we use is equivalent uniform pressure distributions, or reduced foundations. And we use that for geotech a lot. And so we're going to talk, and this is a concept that students wrestle with for some reason, and I'm not really sure why, but we're going to do the best we can. Expressing load in eccentricity and inclination. Let's start with incline loads. We normally divide the load by, I say divide by the inclination action. We split it up into its two horizontal and vertical components. It's vertical component, horizontal component. And we use we use the horizontal, the vertical component will enter to the eccentricity. The horizontal generally doesn't. So we'll start with that. Then we come up with a total vertical load P, which is somewhere either at the centroid, or for a concentric load, or an eccentricity, it's a distance E in either one or two directions from the centroid for an eccentric load. So a total eccentric vertical load has two components. It has a load P and eccentricity E. And then, so what you do is, generally speaking, it makes it simpler to get rid of your moments, as I just said before, and replace those moments with load and eccentricity. And that's how we do that. For continuous foundations, you'll see my notation P over little b or M over little b, and that basically that the load is either in like kips per foot or kilonewtons per meter of load, or a moment in kilojoules per meter or foot-pounds per foot or whatever. And so when you see that, that means that it's per foot of wall. The equivalent footing procedure is this, and it's just described in your book. And it's really very simple, but it complicates. You start out with once you've determined the load and you determine the eccentricity or eccentricities, and you have to be very careful when you do that and make sure that your eccentricities are in the right direction. So, for example, if you've got, it shows in the diagram here, which is one of the more useful diagrams, I think, a load which is, we're going to consider the vertical component only of it, and it's eccentric in the L, along the L, is in the L direction this way, it has an x e sub L, eccentric that way. In this direction, the B direction is e sub B, and either of these can be zero or both can be non-zero. It doesn't really matter. If they're both zero, it's a concentric load. But in any event, once you've established the E sub L, the E sub B, then you can say that instead, obviously, if you push a load off to the side of a foundation or away from the center, you degrade the ability of the foundation to resist the load. And the way we take that degradation into account is we say that B prime, for example, is equal to B minus 2 times E sub B, 2 times the eccentricity. And that L prime is equal to L minus 2 times E sub L, the eccentricity on the length, on the L side. Once we do that, we have a reduced foundation, a foundation which is smaller than the original one, but one where we can actually take and apply our theory to determine whether the foundation will withstand the loads, whether it will meet bearing capacity and or settlement configurations. This is an important concept that over the years my students have struggled with. And I'm not really sure why, but in any event, this is one way that we use. And we use this with things such as bearing capacity analysis, and we're going to get a lot of the ifs, ands, or buts of that shortly. We use it with settlement and all other kinds of things to try to make a simple way of modeling how foundations respond. It was come up, I believe it was Meyerhoff that came up with this. The other approach we're going to take is concerning the sort of ramped approach. The ramped approach takes a little bit different. It basically assumes that the load is uniform. In other words, the equivalent footing attempts to reduce the foundation size to the point where you have a uniform load, which is higher, obviously, as the area is smaller, that represents the higher pressure, lower area that represents the behavior of the foundation. With this, we do a little differently. We say that once you move off the centroid with the load ramps. Well, if we run the statics of this, what we end up is something like this. If you start moving it from the center, you get this result. Starts to a ramp load, but there's still pressure across the foundation. If you get to a certain point, actually here, then that load, one end is 0 and the other one is the maximum. And then once you get past that point, then you get a situation where you have essentially what should be a negative load, but face it, people, we don't have tensile loads in foundation interfaces like that. So those are not permissible. Basically, the computation tells us that the eccentricity for this case is basically equal to 1/6 of whatever B or L we're dealing with the foundation. And basically, since it's 1/6 from the center, it's 1/3 side to side. As a general rule, as long as the resultant of the foundation is within the middle third of the foundation, then this lift-off condition will not happen and the foundation is acceptable. This is an additional criteria which you need to take into consideration with foundations. So let's consider an example of this, an example of one-way eccentricity. It's a continuous foundation, and by the way, with continuous foundations, one-way eccentricity is all you have. I'm not going to worry about the groundwater table. Just see if the resultant force acts in the middle third. The minimum and maximum bearing pressures and the reduced bearing area. Okay, first thing we do is compute the weight of the foundation. It was not included with the load, so we're going to do it. And basically we assume that foundations are 150 PCF, standard concrete. We don't use lightweight concrete for foundations. So we multiply, the width. And we also assume, the other thing we assume is that we don't worry about the fact that the foundation does this and there's a little soil at the top. We just assume that it's concrete all the way from the base up to the top, because most soils run what, 90 to 120 PCF, not that much different from concrete really. So we just do it. So it's 5 feet wide times 1.5 feet high, D, times 150 pounds per foot leads to 1,125 pounds per foot. So we compute the eccentricity. The eccentricity is equal to the M, which was 8,000, which was defined by the problem. We'll go back, let's just check that out. He's got 8 kips per foot, and the concentric load is 12 kips per foot. So we've got actually 2 concentric loads now, because we've got the we've got both the way the foundation, which is concentric, and we have the load from the building, which is concentric in this case. And we multiply that. There is we could also, if we wanted to, well, basically that's basically how we compute E. We essentially take the moment that we have and divide it by the 2, and we get the fact that the resultant load is 0.61 feet away from the centroid of the foundation. Now, to be in the middle third, that eccentricity has to be less than B over 6. Since B is 5 over 6 is 0.833 feet. It's greater than 0.61, therefore it's within the middle third. So therefore, we don't have to worry about liftoff or being outside the middle third. There are 2 different ways of doing this. One of them is to compute the middle third. The other one is to compute Qmax and Qmin. If you can compute Qmax and Qmin, the pressures, one inside the foundation and the other, and then you can, if they're both positive, you're in business. You're within the middle third, as you saw. And if you go back and look at the theory I just presented, you'll see why that's so. So these formulas I'm presenting to you here are basically P plus WF over A, which is actually that should be a area. That is the area of the foundation. P plus WF over the area of the foundation times 1 plus or minus 6 times the eccentricity over B. Therefore, if you did that, you get Qmax, Qmin, and you would know. That's for one-way eccentricity. In other words, if the eccentricity falls on either the B axis or the L axis, then you're in business. For a continuous footing, you only have one. You don't really do an area. You have a B as kind of the area per unit length. So you've got that, and you multiply that times 1 plus or minus 6E over B, and you get the pressures. If we took the same example we had before, and we plug and chug, this is what would happen. The load is 12,000 pounds per foot of wall. The weight is 1,125 pounds per foot of wall. B is 5 feet. If we do 1 minus 6E over B, E is 0.61. We just computed that, and we get 703 PSF. Q max, on the other hand, is the exact same thing, except we change the sign from here to here, and we get 46 PSF. Both are positive, therefore it's in the middle third. So this whole thing hangs together, and you can do it either way, providing you can properly compute the eccentricity. Now, in some cases, instead of giving you a moment and having to do the intermediate stick eccentricity, we will tell you that this load is so far off of the centroid, and this is the eccentricity, and you can compute those. Now, how about the reduced foundation? That's pretty easy since it's in one direction. B is 5, E is 0.61. You plug and chug into the formula that I showed you earlier, and you get B is equal to 3.78. Since it's a continuous foundation, we don't need to consider the effects of length, so we're done. And that's how you compute the reduced. So in other words, you would subsequently analyze this foundation as 3.78 feet wide rather than 5. And we're going to get into the ifs, ands, or buts of that later. With two-way eccentricity, we have a whole different problem. In that we have two different eccentricities. But the middle third concept still applies. It's just that it's a little different. Instead of being just middle third, in other words, just comparing E and L and being done with it, you have this little diamond in the middle. That little, as long as the load is within that diamond, you have an acceptable foundation. It's in the middle third. And that is, it can be to an equation is this one right here. 6E of B over B plus 6E L over L needs to be less than unity. As long as that's true, you're within that diamond. Now, one mistake that I have seen in students' works is that they'll compute an eccentricity in one direction, they'll compute an eccentricity in another direction, they both match, and they'll declare victory. But that doesn't take into account the fact that if it's in these little regions right here next to the flats, then it's out of the middle third. So when you've got two ways of eccentricity, use this formula right here to make sure that you're in there. You can compute, obviously with a two-way system, you don't have just eccentricity at the center, at two edges. You've got it at four corners, and four corners of eccentricity will give you you have four different corners. Therefore, you've got four different pressures to compute if you go that route, or if you're asked to do it. So therefore, this formula down here gives you, for a rectangular foundation, and it works for a square foundation too, for that matter. If you've got you can have a situation with a square foundation where you have eccentricity in the B direction and eccentricity in the L direction, which is the same as B, are different. Just because a foundation is the same dimension doesn't mean the eccentricities are. But this formula will give you the pressures at the corners. And if any of those pressures are negative, that means the foundation, that the resultant is outside the middle third and is unacceptable. So let's go with a two-way eccentricity example, which is one that's a little tricky and has some interesting implications. It's basically a grain silo. Each silo has an empty weight of 29 meganewtons. It can hold up to 110 meganewtons of grain, and the mat that's all sitting on is 60 meganewtons. And obviously, they can load the silos independently of each other. Find out if basically you're trying to outsmart their ability to load the foundation, whether or not eccentricity with the various load combinations possible. We can eliminate, for example, there's a couple of load we can eliminate right off the bat, and that is if they've loaded these two silos or these two, in other words, opposite corners. That's going to result in an concentric load. Obviously, loading all four of them will result in a concentric load. The two that we're going to take special interest in is we load them on one half over here, or we load one in the corner. Obviously, 3/4 is going to give us not quite a concentric load, but a more concentric load is, say, you're just loading this one or this one. The two worst cases are those, and we're going to talk about those. So let's talk about two-way eccentricity. Example. And we're going to talk about one-way. If we load these things on one side, we're going to have one-way eccentricity. So Q is equal to 4 times 29. That's always there. And 2 times 110, 2 silos are loaded, plus 60, the mat, is 396 meganewtons. And then M, the moment, is equal to the 2 times 110 times 12. And this diagram kind of stinks in some ways, but the distance from here to the centroid is 12 meters. From the centroid of the silos to the center line of the whole thing is 12 meters. So therefore, what do? Eccentricity is moment over load. I simply do that. And again, eccentricity of 6.67 meters in one direction. In this direction, there's no eccentricity. So therefore, the B over 6 is equal to 50 over 6. The maximum eccentricity is 8.33, which is greater than 6.67. So we're still in the middle third on that loading. Now that you would think that this would be the most, the conventional wisdom would say that, well, that's the most because you've got over on one side. That's not the case, however. If I only load one of these silos, then this is what happens to me. I have eccentricity in two directions to start with. E sub B is equal to E sub L. The only difference is that my P is lower, and which is basically because I took one silo out from the last one. So I get 286 meganewtons. My moment, I have two moments. I have a moment for one axis, the B axis, and a moment for the L axis. Even though B and L are the same, and the moments in this case happen to be the same as well, but they're two separate moments, is equal to 1320 meganewton per meter. But what that means is that the two eccentricities will be the same. So I compute them. M over Q is equal to 1320 over 286. I get 4.62 meters of eccentricity in both ways. So what do? Well, just for the quick and dirty, what I do is I put 6 EB, I use the little formula that I gave you earlier, and 6 EB over B and 6 EL over L. You plug it in, I get 1.11, which is greater than 1. I am in trouble because basically this is an example of how your conventional wisdom can lead you astray on a problem like this. I actually have an eccentricity problem with just one silo loaded. If they had actually loaded the two silos, and it's possible also that they would load one silo and then they would load the other one. So what do? I continue on. I've got several options. One, the easiest, the simplest option would be to enlarge the base of the foundation. And that's basically what I propose to do. Now, increasing the size of the mat does increase the weight of the mat. And that would definitely impact bearing capacity and settlement. However, I don't, I would actually the eccentricities will be altered with the, I've got a chicken or egg problem. As I increase the mat, the weight increases, which would change my which would actually lower my eccentricity. Generally speaking, the weight of a mat, most of which are concentric in their configuration, weight of a footing or a mat will generally tend to decrease the eccentricity of the load. But just for the back of the envelope, what I've done is I've ignored the increase in the mat in the weight, and as a result, I've gotten something quick. So I can do that. I could play around with the increase in the weight and whatnot and come up. I would have to use some kind of goal seek, but this is a good place to start. That would be the obvious way of increasing is to deal with the eccentricity, is increase the size of the mat. When I go to compute the equivalent foundation, I'm just going to take the 55.4 meter result as it is, and I plug into my formula B minus 2E for both, and it's the same of both because the eccentricity is the same and the B is the same, and the B and L are the same. And I get a reduced size for analysis purposes of 45.8 meters as L and B as well. So that's how I would achieve the, once I've actually done the expansion of the mat, then I can use those dimensions to check my bearing capacity and settlement. With one-way eccentricity, it's a little simpler. We would actually, it's simpler and more complicated. With the example I just went through, you've got a situation where both B and L increase, and the eccentricities are the same. Therefore, you're going to end up with an equivalent square foundation with the same aspect ratio as the one you had before. Well, unfortunately, that doesn't work that way with if you've got an eccentricity in just one direction. In this case, the E sub L is 0, and the E sub B is 6.67. Therefore, even though the L will stay the same, L and L prime are the same because there's eccentricity in the L is 0, the B will actually shrink down, and you'll end up with, what you've basically done is you've turned a square foundation for geotechnical purposes into a rectangular one. And that is the result that you've got. So in these problems, you kind of have, I've tried to show you different scenarios where sometimes what you think should happen doesn't happen. We've discussed an example of the eccentricity, and we've talked about the reduced foundation size. And I said that there's some little ins and outs about that we need to discuss. Well, here we are. We need to discuss those. There are as you saw in the last example, it is possible to change the aspect ratio of a foundation in the process of using its reduced area with eccentric loading. And that's brought up a lot of interesting discussion, if that can be, about this particular topic. Because if you change the ratio of B to L, you will change the shape factors. If you change the shape factors, you will change the bearing capacity without necessarily, in a different way. There are two ways of handling those. The AASHTO guidelines recommend if you use those, if you go with B prime and L prime with reduced foundation size due to eccentricity, then you should use those for the shape factors, and just use those are the effective footing dimensions to be real footing dimensions, and that's the end of it. In the days when these were formulated, that was not necessarily what the original researchers who looked at it had in mind. And they would actually require you to use the shape factors from the original size foundation. In this class, either is acceptable, and which one you use depends upon who is, what code and environment that you're in, engineering practice environment that you're working in. Another issue which really we kind of able to get around is combining shape and inclination factors, and many have recommended some have recommended like bowls not to do this, and you can be thankful that I didn't make you use bowls for your textbook. I don't think that if we eliminate the problem of using inclination factors, we eliminate this problem altogether. And we've done that. I think the best way is to use a vertical horizontal component and analyze the foundation that way. The next topic we're going to look at is foundations on slopes. And this is a topic that it's a little tricky. The method's a little tricky. It goes back a long ways, but and I believe it was Meyerhoff developed this also. That it attempts to address an issue which I think instinctively we know that it's not a good combination, but it's one which is frequently unavoidable, and that's putting a foundation on top of a slope. And basically what you do is the easy way to do it is to follow the procedure in the book. The book gives you a somewhat detailed description of how to implement this method with this foundation on a slope. And it gives you an equation here which shows how this is computed. The tricky part with this is using the charts to determine what the different factors are. The rest of them are fairly straightforward, but like I said, using the charts is a problem. So for example, you have a strip footing be constructed on top of a slope. The soil properties are purely cohesive. C is equal to 75 kPa, 18.5 kilonewtons per cubic meter. Water tube is very deep. The H is 8 meters. The B is 3. Follow your variables very carefully. You've got they're given right here. I'm sorry. They're given right here in this. You need to follow those very carefully. So find the ultimate bearing capacity using the method of the previous slide, which again is also given in your book. H is greater than B since 3 meters is less than 8 meters. You obtain, now the figure 4B I think is left over from DM7. Which is what I used to use to teach this course. And basically 4B is this and 4A is that. That's where they got it from, as you can see right here. And so therefore that's what we use. We're actually using this particular case because the slope is right here. If it's further down the slope, you have to use this one. But we're using these right here. And we can use these to compute the NCQ is used by this chart, the A chart, and gamma Q is by the B chart. So therefore, my apologies for not updating the slides quite as well as I'd like to. We need to obtain NCQ, and with N not is equal to 0 as the chart method indicates. So D over B is equal to 0.5 and little b over big B is 0.667. You do a linear interpolation for this at D over NCQ for D over B is equal to 0 and slope angle of 30 degrees, which is what we have, is 4.9. NCQ for D over B is equal to 1 and slope angle is 6.4. Linearly interpolated NCQ is equal to 5.7. Then N gamma Q is equal to 1 since the soil is perfectly cohesive by the method as described earlier. B over 2 is equal to D. The shape factors are unity since it's a continuous footing, and we don't consider water and that kind of thing. So therefore the Q ultimate is basically a plug and chug into the previous formula, and you get the results of 455.25 kPa, and you multiply that by the width to get the load in basically kilonewtons per meter. One of the things that you should, in many ways, design is a good example of is something which you have it's better to try to avoid problems than it is to actually have to deal with them. And the further back you can, there are certain building codes which require you to set footings back from a certain distance in order to meet the code. And that is largely to avoid problems, because most slopes by their nature, and we learned this last semester in slope stability, are in soil mechanics, are unavoidable, are unavoidably unstable up to a point. In other words, there's always something that's trying to force the slope downward already before we even get to putting something on top of it. You put something on top of it, it only makes matters worse. So the further you can set a footing back, the better. And this is a description of that. Your book is really good about your soils and foundations reference map by giving some practical considerations in the design of things. They have quite a few here. I'm going to concentrate on three of them. First of all, review the soil test data to determine the unit weight. Obviously, it should be obvious by now, no matter what variation of slope stability of bearing capacity equation you're using, is that the more Coulomb triple, the unit weight, the cohesion, the internal friction angle, plus all the other things, the groundwater table, all that, and the general stratigraphy, are essential to know that to design properly a foundation. And the solid foundations are no exception. The only difference is the depth that is critical to the entire operation. So it's very important for you, if you're interpreting soil data, to make sure that you've interpreted the soil data to come up with these properties. And we're going to talk about this towards the end of the course, most boring data, and certainly any geophysical data, doesn't specifically spell out what the more Coulomb values are, particularly in view of the unit weight. The unit weight is one that's usually, it goes AWOL the most often. Usually what you'll have, unless you really do well and get something like vein shear data and that sort of thing, would be SPT data. SPT data must be reviewed carefully. With cohesionless soils, sandy soils, SPT data can be very reliable to determine properties such as unit weight, friction angle, and all that. Cohesive soils, that's a different story. You have to be very careful when you use them. So that's the first thing. The second thing is called mobilizing the resistance of the soil. We'll talk more about this when we get to deep foundations, but generally speaking, it takes quite a bit of even though the theory says that it's a purely plastic process. In spite of that fact, it takes a fair amount, in many cases, a fair amount of deflection to fully mobilize the plastic, the shear that would induce plastic failure for a bearing capacity failure. As a result, it is very advisable to run a settlement analysis, and particularly as the foundations become wider, you will discover that the settlement analysis basically drives the design as opposed to bearing capacity. So that's something you should keep in mind. And so, bearing capacity is very frequently designed with very conservative factors of safety in order to take that large mobilization distance into account. But very frequently also the settlement factors will preempt that, and actually you'll end up with a lower factor of safety for bearing capacity based on settlement analysis than you on the bearing capacity. So the last one is something which I have not. There are two different, and books treat this problem differently. There are two different two different bearing pressures. There's the gross and the net. What we've been teaching you now up to this point is gross bearing capacity pressure. In other words, we take bearing capacity pressure. It's based upon, you get bearing capacity pressure off of the triple N formulas is basically gross. If you want to compute net, you take out the overburden pressure between the base of the foundation and the top of and the surface of the soil. What you will see this issue handled differently in different books. Your textbook, the Soils and Foundations Reference Manual, basically states here that it is overly conservative to use net bearing capacity as a general rule. You need to read that carefully. Other people have different opinions about this. There's not that much difference between them. My own personal opinion is that for most foundations, the difference between the two is not very high, and as a result, if you're that exact, I would stick with using gross for an ultimate. I think the book's approach is correct in that regard. With bearing capacity failure, you've got a failure surface that starts on the edge and it loops around and comes back up. And I'm kind of exaggerating that to make it easier to see. In both cases, so basically you have to think about where that failure surface is. And that can be important if you've got weak layers, if you have it for this direction, and adjacent structures if you have this direction. The general upshot of this, and I would read this part of the book, is that for the larger, the higher the internal friction angle of the soil, the deeper the failure surfaces go and the further away from the foundation it goes. And there actually is a little chart here which shows you the relationship between the two. With the groundwater failure thing that that they use is where really this comes in, and that's a very conservative implementation of that. So I would, obviously if you're designing and you've got weak layers under there that you're trying not to intersect the failure surface with, or you've got adjacent structures, you need to keep the location of that failure surface in mind if you're dealing in that tight a quarter, so to speak. Oops, wrong way. Okay, presumptive bearing capacity. Presumptive bearing capacity until, I don't know, when building codes started to be drawn up, even before then, presumptive bearing capacity was pretty much the way in which shallow foundations were designed. Prandtl's methods and Tersaki's propagation, the same, didn't come along until, I said, the 40s, maybe the 1930s and 40s. Until then, building codes would say you will, for this kind of surface, this kind of structure, on this kind of foundation, you will limit the contact pressure to such and such. And usually it was a conservative value. Sometimes, if the conditions didn't match or the codes were off, it could be an unconservative, but usually it was pretty conservative. Presumptive bearing capacities also took into account settlement issues, which were not fully understood then either. So, in soil, I think that presumptive bearing capacities are out of date. I believe that I would not use them as a design technique. In some parts of the United States and some places in the world, you will still see them enshrined in codes, and you have to work around. I said that, just because you make code doesn't mean you've got a good design. But on the other hand, that doesn't mean the converse is true. To have a good design, you've got to meet code. And if code is more conservative than your calculations, you better use the code, or your design will be kicked back at you. So you'll see that. With rock, it's a different story. Rock is, you still see more often rock used, presumptive bearing capacity used in rock. And we've got a long narrative about this. The key to understanding the issue with rock, and something that if you've run, and my students have done this, have run the rock quality designation test, the RQD test, you will note that not all rocks are the same, particularly if you're in an area like weathered rock, and UTC is certainly an area with a lot of weathered rock. Then you understand that just because it's rock doesn't mean it's solid. And so therefore your rock quality will vary, and if your rock quality varies, the ability of a foundation put on it to carry load likewise varies. And so we've got a lot of interesting information in there. And by the way, one of the things that I try to compensate for is the fact that many soils textbooks kind of give the short shrift to rock topics of any kind. I think this is a mistake. This is especially a mistake in the area that I'm teaching in and living in, where we have a lot of rock of wildly varying quality, plus we've got the karst topography with the sinkholes. I think a certain understanding of rock is essential. And so therefore we have different recommended bearing capacities, allowable bearing pressures based upon different types of purely empirical correlations over the years. The one that I want to really focus on is, obviously these can be very useful in rock, because you don't have in rock classical bearing capacities. Failure in rock is a very complicated subject. Rock is both the best engineering material, and sometimes it's the worst. And the reason why it can be the worst is because rock is frequent, even solid rock has fissures, and it's a natural material and has fissures and failures. And that's true of your granite countertop too. If you have one of those, you may have some fissures. You may, fissures and failures in that too. It has weak spots. Most granite countertops have somewhere. So it's because it's a natural material from the earth, and it's going to have those things. You get fissures, and if you get failure along those fissures, very solid rock can do some very nasty things. Probably the most visible thing it can do is have a rock slide, which we see in this part of the United States on an all too frequent basis. We see rock slides. But for presumptive bearing capacities can be very useful in rock. And in fact, one of the more interesting, the one we're going to focus on, is this one right here. About presumptive bearing capacities in rock based upon the RQD. Now, it makes sense that the higher the quality of the rock, no matter what kind it is, the higher the presumptive bearing capacity is. And that's exactly what that table says, because the table actually varies from, say, at 0, it has, a soil-like, it's only about 20 KSF, up to about 400 for 100% quality rock. Allowable, by the way, those values, and it's important to note, are allowable values. Those are not ultimate values. Those are allowable values. And it's fairly easy to compute by F, pressure allowable times A, where you can get an allowable load for a foundation, or size of foundation for an allowable load based on a presumptive bearing capacity. Well, that pretty much concludes this part of it. Again, thanks for watching, and God bless.